Mic check. Mic check. Everyone's hearing me? Alright. Okay. Let's start today with problem set 4. What I'm going to do is that the first few problems in problem set 4 are going to be more like on the bilinear transform and impulse invariant design. But like when we hit to like question 5, 6, and 7, these answers actually are somewhat detailed, so I wouldn't really bother to go through them that much, especially question 6, which is like the sketch. Question 7 is just a reason question. I'll explain this a little bit, but basically the bulk of the questions that we're going to be doing today will be questions 1 to 4. In particular, these questions that you're seeing here from 1 to 4 is like what you might expect on your final exam, because you will always be tested on the bilinear transform and the impulse invariant design technique. Alright, so split this here, put that there because I have to write solutions. Okay, so the first question here is asking for us to do the bilinear transform on this h of s equation here. And they basically told us that the transfer function for the analog filter here with a omega c of 1 radian per second is given by this h of s equation here that we can see. They also give us the digital cutoff frequency here for what we need to design to, which is 500 Hz, and the sampling frequency that we need to use, which is 15 kHz. So the first thing that we want to do is that we want to start with the h of s equation. Okay, so hold on, put that here. Question 1. So we know h of s here is given in the form of 2 on the numerator, then 2 s cubed plus 4 s squared plus 4s plus plus 2. Immediately we can see that if we factorize 2 from the numerator and the denominator, we can reduce this into a more simpler form. So this entire thing here can reduce down to 1 on the numerator, because we're extracting 2 on the numerator and the denominator. The s cubed will become 1, this will become 2, this will become 2, and this one here will become 1. So the next step is that we're required to match the 500 Hz for the digital filter to the 1 radian per second for h of s, or analog filter. So we know that basically, if we need to find for a digital frequency, which is capital omega, the associated equation for this is going to be 2 pi fc on the numerator divided by fs. So 2 pi the cutoff frequency divided by the sampling frequency. So what this is equal to here is that it's going to be 2 pi multiplied by our cutoff frequency, which is basically 500 Hz divided by our sample frequency, which was 15 kilohertz or 15,000 Hz, which will basically give us, if we do reduction here, well, I'm keeping it in terms of pi for now, it's going to be 2 pi divided by 30. Because we're designing for a low-pass filter design, that means we'll be using the low-pass filter analog frequency equation. And this equation is given by FA is equal to C on 2 pi tan of 0.5 capital omega. We know that if it was for the high-pass filter design, it will be a different equation. When instead of using tan, it will be cotan and so forth. So because we just now calculated for capital omega here being our digital frequency, and we know what our analog frequency is going to be accordingly, because our analog frequency was given by the normalized low-pass transfer function here, that means we just need to calculate for C accordingly. So if we substitute in capital omega first, copy this here. The 0.5 multiplied by 2 pi divided by 30 here will just give us 2 pi by 30 by 0.5 means that this will just go to pi on 30. Put this in proper brackets. And then we can rearrange the equation to make C the subject of the formula. So C here will be equal to 2 pi FA divided by tan pi divided by 30. And by the time we substitute in our analog frequency and so forth and whatnot, this will end up resolving to 1 divided by 0.105 equal to 9.51. Now the reason why the 2 pi f here, the 2 pi fa here resolves to 1 is because 2 pi of the frequency will just give us the omega, and this will be our analog frequency here. So the analog frequency which was given to us was omega c is equal to 1 pi radians per second. So 2 pi fa here will just resolve to 1. Tan of pi on 30 will be this 0.105 here, and the division of 2 will end up giving us the 9.51. So for the low-pass filter design, we also know that we'll have to use S in a particular form. So S for the low-pass filter design is equal to C multiplied by Z minus 1 divided by z plus 1. And this basically is going to be 9.51 because we already have c. Multiply by z minus 1, z plus 1 on the denominator. And we're substituting this into h of s, and we need to simplify it. So, in doing so, this now becomes h of z here, because the entire equation is in terms of z. And this now becomes 1 divided by everywhere we have a s, we're going to be substituting accordingly. So this is going to be 9.51 into z plus z minus 1, z plus 1. Okay, we'll just make that look a little more neat. 9.51 z minus 1 into z plus 1. And this entire thing here is going to be cubed plus 2 into 9.51 z minus 1 z plus 1, and this here is going to be squared plus 2 into 9.51 z minus 1 z plus 1 plus 1. So s equal to c multiplied by z minus 1 divided by z plus 1 is for the low pass filter design. For the high pass filter design, it will be c multiplied by z plus 1 divided by z minus 1. So depending if you're designing for a low pass filter or a high pass filter, the design changes accordingly. Also, the equation for f of a here will also change accordingly, depending if it's a low pass filter design or a high pass filter design. For the low pass one is tan, I think for the high pass one is negative c divided by 2 pi cotan of 0.5 capital omega. Right, so now we have each of them in this long form here. The thing that we want to do is we want to make sure that this resolves into a proper fraction. So that means the highest power of z here on the denominator of the denominator is going to be z plus 1 all cube. So that means we need to multiply the numerator and the denominator by z plus 1 all cube. So multiply numerator and denominator by z plus 1 all cube. Each of z here are resolved into z plus 1 all cube, and then this will be 9.51 here, 9.51 cubed into z plus 1 cubed plus 2 into 9 . 9.51 here squared into z to the minus 1 here, all squared. Because we're multiplying by z plus 1 all cube and there was a z plus 1 all squared, that means the remainder here is going to be a z plus 1 on the numerator of this part here, plus 2 into 9.51 into z minus 1 z plus 1 all squared plus z plus 1 all cubed. Okay, well, I reduce this a little bit. Right. And then it's just a matter of multiplying out all of this on the denominator here and cancelling and whatnot and so forth until they get it down to a rational form. So, marks for this question in particular, like this, could come such that it would be, this could be a 10-mark question. Oh yes, that's correct. This here is supposed to be z minus 1 all cubed. Z minus 1, yeah, right. So yeah, that's correct. Thank you for that, pointing out that mistake. F of A here is basically the analog filter frequency, or the analog cutoff frequency. And 2 pi f of A here is basically, if you're saying anything that's 2 pi f is basically our omega. So 2 pi f of A is going to be omega E. And we know from the question here that for this analog filter, they gave us the cutoff frequency here, which is going to be 1 radian per second. So the entire 2 pi f of A here will just equal to 1, because this is omega E here as well. Alright, so marks for this question in particular, this tends to come like about like a 10-mark question. The mark breakdown would be such that you'll get marks for calculating omega here, which might be 1 or 2 marks. The other 1 to 2 marks here will be calculating for C. Then the remaining 6 marks will be doing the substitution and resolving h of z, because this is where the majority of the work is going to lie. Now, we do expect that in doing this reduction here that some mistakes are going to be made, so we try not to heavily penalize you regarding for this. Once you did a good attempt on the working, you'll get most of the marks here for the reduction. Alright, so question 2. Any other further questions on question 1 here before I continue? typically you need to reduce it such that you have it in terms of descending powers of z. So that means you'll have to fully expand it out and you'll have to go on and so forth to actually reduce it. Now, this question is hard because the transfer function is up into the cube realm, and this tends to take a while for the reduction to actually occur. Typically, we try to make sure that the transfer functions are more like around the square, so the s squared terms, so that way you don't have to do all this kind of work into for the reduction. But like I said, the majority of the marks is for doing the reduction here, and we do expect you to make mistakes when you're doing the reduction. So we tend to be a little more forgiving here for when you're actually doing the reduction, and we'll give you like a little more leeway with the marks when you're actually doing this part. The numerator itself needs to be expanded out as well. No, this, you don't need to do partial fractions on this. This is just once you have it in terms of z, that's it. So you just expand it, and you have it in descending powers of z. So like, in this case it will be z cubed plus z squared plus some z plus some constant z. The same thing on the denominator. Alright, so question 2 here is asking for us to design a 15Hz digital filter based on the HFS transfer function here for a butterworth low pass filter using the impulse invariant technique, and we assume a 100Hz sampling frequency. I don't know where this part would see new question 10 here, but that's not supposed to exist. That could get striked out. Yeah, that part not supposed to be in the question. That might have been a typo when I was modifying it. Alright. So, in doing question 2 here, we start with our h of s equation. And because we're doing the impulse invariant design technique, this means we actually have to do partial fractions for this. So the equivalent partial fraction for this, because I'm just going to give you guys the answer in effect of time, will be 6.3 into s plus 6.3 minus 6.3 into s plus 1327. And then we get this back in terms of h of t, which is going to be 6.3 into the exponent of minus 6.3 t minus 6.3 multiplied by the exponent of negative 1327t. We also know that our sample frequency here was 100 Hz, which also implies that our t here, being our sampling time, is going to be 1 divided by 100, which is 0.01 seconds. So once we have it in terms this sampling time here, we can transform our h of t here into h of nt. Or if we wish to shortcut it, we could just say that this here is h of n is equal to 6.3, and everywhere we had t here, we just put in nt accordingly, n capital T. So this is going to be 6.3 exponent of minus 0.63 n minus 6.3 exponent of 13.27 n, negative 13.27 n. So then we could separate out the powers here accordingly for the exponent, and this could go down to 6.3 of, so let me copy this just to make life easier. So you can say 6.3 here of this part here, and this entire thing here will just go to the power n. And similarly we could do this as well for the exponent here, and so forth. So this is just basically we just splitting the powers here accordingly. So h of n here will be 6.3 into 0.939 to the power n minus 6.3 into 1.72 by 10 to the minus 6 of the power n. Then we need to transform this h of n here into z. Oh, so the purpose of the impulse invariant design technique is that you start off with the h of s here. You need to get this in terms of h of t. Push this into h of n because you have a sampling frequency. So you get this. You get the sampling time from the sampling frequency. You put it in terms of h of n, and then from h of n you transform into h of z. That's just how the impulse invariant design technique works. So it comes like you do a more roundabout fashion when you're doing the impulse invariant design technique. So h of s to h of t, then to h of n, then to h of z. So the associated transform for these parts here will be the e of n, e to the power n transform, which is basically going to be z or divided by z minus a. So in this case, h of z is going to be 6.3 multiplied by z into z, sorry, divided by z minus 0.939, and the 6.3 into z divided by z minus 1.72 by 10 to the power negative 6. Yes, h of n and h of nt are basically the same thing. It's just that we know what t is. So once you know what t is, you just have the entire equation in terms of n. T here being capital T. That's right. Now, one thing to note here is that this value here is really small. Okay, that's like an extremely small value. So we could just basically say this entire value here approximates to 0. And in this case, this part here will just end up being z divided by z, which will be 1. So approximating small values to 0 . I'll just copy this for the simplicity. So this here, if the equation decides to behave, will just become 0. And because that becomes 0, that becomes z divided by z. Z divided by z is 1. So that has become 6.3. And this makes our lives a lot easier, because now this gives our expansion here a very simplified form. So if we expand this out, we get z minus z plus 5.92 into z minus 0.939, which will be equal into 5.92 divided by z minus 0.939. And then if we want to make this into the causal form where all the powers of z are negative, that means we just get rid of all the positive powers of z. So the highest positive power of z here is z to the 1, so we multiply by z to the negative 1 on the numerator and the denominator accordingly. So we'll go 5.92 z to the minus 1 divided by 1 minus 0.939 z to the minus 1. And that basically is the end of question 2. So, any particular questions on question 2 at this point? Yes, Z tables are provided to you in the exam. And you are allowed to do these kind of approximations here to say small values go straight to 0. It matters depending on what the question asks. So if the question asks for like the causal form, that means the Z powers here need to be all negative. If it doesn't ask for the causal form, you could just leave it in this form here. That's acceptable. I think safety-wise, you should also always put it in negative powers of Z, because typically you'll be working in positive powers of Z throughout the entire thing. It's just only one step further just to put this in negative powers of Z. Alright, let's see. Alright, so question 3 basically is asking us here to use the bilinear transform to design equivalent high-pass filters based on the question 1 prototype here and the question 2 prototype here. So I'm just going to show you like what is going to be the key differences if you're actually going to be doing the design technique here for the bilinear transform. So for a high-pass filter design, the f of a equation here will change accordingly. So f of a here will be equal to minus C divided by 2 pi of cotan of 0.5, no, not tau, is it here? No, it's not here. Right. So this will be our f of a equation here, minus C divided by 2 pi multiplied by cotan of 0.5 capital omega. The way how we calculate for capital omega will remain the same. So that would be, we have this here. The analog frequency cutoff in terms of omega being omega A for the analog frequency is 1 radians per second. That will also remain the same too. The FC for the digital side is going to be 500 Hz, so that remains the same as well. So what happens here is that when you solve for C, here when you rearrange the formula, it's going to be minus 2 pi f of a into cotan of 0.5 multiplied by 2 pi divided by 30. Oops. And in doing all this calculation here, C here will resolve to 0.52, an entirely different value from what you saw on top here. The next thing to note is that the substitution for S is also going to be different for the high-pass filter design. So for a high-pass filter design, S here is going to be equal to C all multiplied by Z plus 1 divided by Z minus 1. So this here is basically going to be negative 0.52 multiplied by Z plus 1 divided by Z minus 1 into H of S. You do the same thing as before, where you have it in this form here, and you just multiply out, substitute and simplify, and you get it back in terms of H of Z in descending powers of Z. The same process is also used for the second equation here, because they ask you to do the bilinear transform. You do the same steps with f of a. You calculate for capital omega, so I'll just do this because capital omega here is going to be a little bit different. So this would be question 1 of Q1 for HPF design of Q2. Our capital omega here is going to be different because we have a different cutoff frequency, a different sampling frequency. So our cutoff frequency in this case was 15 Hz because we're designing for a 15 Hz digital filter. And our sample frequency here was 100. So this entire thing here, I'm just leaving it in terms of pi for simplicity, would be 6 pi divided by 20, and this can reduce down further into 3 pi divided by 10. FFA will also follow the same equation because it's for a high pass filter design. And we can rearrange this equation to make C the subject of the formula. In this case, this will be 3 pi on 10. And this entire thing here will resolve. Oh, whoops. Forgot one thing. Our f of a here was minus 2 pi f of a was minimum 1. Our f of a in this form here is also 15 Hz. So this here will be 2 pi by 15. So this here will resolve down to minus 48. Well, approximately, give or take. There may be a decimal regarding this. And then the next step will be to substitute this into the h of s equation for question 2. And just simplify it as quantity as well. So for high pass filter designs in particular, remember the f of a equation here will change accordingly, and the substitution for s will also change accordingly as well, because instead of it being z minus 1 divided by z plus 1 is now z plus 1 divided by z minus 1. No, because this question asks to use the bilinear transform explicitly for the question 1 and question 2 analog prototypes. So a question that may arise is that they gave you the transfer function for the third order normalized low pass filter and they gave you a cutoff frequency here. When I put in stuff in terms of NT is because of the impulse invariant design, but when you're in the bilinear transform, you'll be doing the equation say with f of a and c and doing the substitutions here accordingly. The impulse invariant designs when you go from h of s to h of t, then to h of n, and then to h of z. Right, so for the bilinear transform, and if you design for the high pass filter design, remember the f of a equation here will change accordingly. You'll have to calculate for c as normal using this adjusted f of a equation. And remember when you're substituting for s, the s form will take a different approach. So for the low pass filter design it was z minus 1 divided by z plus 1. The high pass filter design is z plus 1 divided by z minus 1 here accordingly. Alright, so question 4. See, I have some mistakes here. This is to be part A and part B. I'll fix that accordingly as well. And just highlight that in the meantime. Alright, so question 4 here. We have a h of z filter equal to 0.318 plus 0.5 z to the minus 1 plus 0.318 z to the minus 2. So this is a moving average. No, this is an averaging filter, not a moving average filter. Because if we transform this into h of n, because the z equation here is in descending powers of z, we can do a straight transform here, which will be 0.318 plus 0.58 delta of n minus 1 plus 0.318 delta of n minus 2. The Hamming window, and typically is normally given to you, but you actually could just refer back to this in your notes, is given by w of n is equal to 0.54 plus 0.46 cosine of 2 pi common n divided by capital N minus 1. And because we have 3 terms here, this means n here is going to be equal to 3. So capital N here, because we have 3 terms in the filter, is going to be 3. Next thing we need to make sure is that the window must be aligned symmetrically to sequence to scale endpoints automatically. So this means that for common n, this will go from -1, then 0, then +1 to accommodate for all 3 values of capital N. Right, so let me open a new window here. I'll have to use Octave here for a little bit. Alright, so we want we need to define our n here, so n is from -1 to +1. And then we have to say w of n plus 1, because we have that negative index and not being accepted by Octave by 4, 6. multiplied by cosine of 2 by pi by n divided by capital N was 3, so 3 minus 1 is 2. Okay, so this needs to be w of n plus 2. And we get our w equation coordinates, sorry, not coordinates, w equation coefficients here accordingly. So if we minimize this means w of n here is equal to 0.08, then 1, then 0.08. And then the next step will be h of n multiplied by w of n. And this basically means that we take each one of these coefficients here, so this first one, the second one, and this third one here, and we multiply them accordingly by the w of any coefficients as well. So this will be 0.0, 0.08, sorry, 0.318 multiplied by 0.08, 0.5 multiplied by 1, and 0.318 multiplied by 0.08. So h of n multiplied by w of n is equal to 0.025, 0.5, 0.025. And then if we put this in terms of z, this will be 0.025 plus 0.5 z to the minus 1 plus 0.025 z to the minus 2. And that basically is the end of question 4. Alright, so any questions regarding question 4? So this is basically an averaging filter because it was already arranged in descending powers of z. So once you have a h of z equation in this form here, from z to the 0 in descending powers of z, this is of the form of an averaging filter. If it was a moving average filter, this means that we could have extract out a particular coefficient here, and we can say 1 divided by that, multiplied by the remaining coefficients here. But you could just say it is an averaging filter and it basically conveys the point. You won't lose marks for that. And because it also follows that it's this general form of h of z here, when you do the inverse z transform, it's just basically each delay here is going to be like delta of n minus 1, and this delay here for z minus 2 is just going to be delta of n minus 2. So this works when you just have h of z in this form here from z to the 0 going down in negative powers of z. So this is just a general form that you'll need to memorize for averaging filter. Alright, so questions 5, 6, and 7, they're basically already done with regards to the problem set solutions. So I'll post those up after when I'm finished here, and for you guys to watch, so that way you can see actually how to attempt question 5 and question 6, because they are kind of pretty long to actually do. Question 7 is a very simple reason, and the reason for question 7, I have it in the problem set as well, but I'm telling you guys why, is that they're asking why the impulse invariant design technique does not work for analog prototype being used is a band stop or a band pass. And the reason for this is that the impulse invariant design technique, it tends to preserve the impulse response of the original analog filter by digitizing the impulse response of this filter. But however, it does not digitize its frequency response. And this method is inappropriate for high pass or band stop filters because since it does not take into consideration the frequency response, aliasing can be inherent for the design of the filter. So the explanation is written in the problem set solutions, so for you guys to actually watch and see how it is. But the visual way to see this is that when you watch the magnitude and frequency responses here for the impulse invariant design from the lecture, you would see that one is preserved, whereas the other one is not preserved. So I think in particular the frequency response, when you're watching it, the frequency response is not preserved when you're doing the impulse invariant design technique. So because that response is not transferred across equally, you can have possible aliasing using this design technique. And as of such, the filter won't be designed properly. Right, so that basically brings us to the end of the 4th problem set. Any general questions you guys have at this point, please let me know in the chat, that we can address them one time. It probably does, but I realized that I did probably possibly put up the wrong problem set with all the extended questions and so forth. This is actually the optimized problem set that we need to really be focusing on, because it's just basically the same types of questions that you're going to be getting regardless. impulse invariant design technique and bilinear transform is pretty straightforward. Once you know the steps, you're pretty much okay. The hardest part about it is extracting out what is going to be the analog frequency, the digital frequency, and the associated cutoff frequency. I'm not too sure as yet. I know Fazal was thinking of if to give you guys an open book final exam where we release the exam online and you have about like 24 hours or 48 hours to actually attempt it on paper, and you just take snapshots and you send it back to us. But I figure that might end up being eventually what he's going to do, given that we are on extended clues here at this point in time. But you will get an official response, probably on my learning or probably from me or Fazal, when that decision is made. And like I said, chances are it's going to be an open book final exam. I think they have a meeting with the dean either today or tomorrow for finalization of that decision. Yeah, quite possibly the question 7 on that one, specifically for this course. It's quite possibly that the question 7 on my learning is actually the question 10. The question 7 here, sorry, is the question 10 on my learning. I'm gonna log in and check just to make sure. Set 4. Yep, it is. Because in the old problem set, we no longer do single frequency sinusoid waveform generators and DTMF transceivers and JPEG compression. Those were topics that were tested like years before, but we're no longer testing those topics, so those questions became irrelevant. So that's why we only have up to question 7 here. I'll re-upload the problem set accordingly, so that way you guys can actually see where it reflects. One thing to note is that the solutions I'm uploading are Fazal solutions, and they have one or two little minor errors. In particular for question 2 and question 3, where he's calculating for capital omega and C. So just pay attention to what we did here in the video accordingly, and this is actually the correct way to calculate them, because you have small little arithmetic errors when he's going through them. But yeah, so reiterating, specifically for this course, you guys may end up getting a open book final exam, where we will give you our official response once the decision is made. If it is an open book final exam, we will tell you the date and time when the exam will be uploaded on my learning for you guys to retrieve. I will be given a 24-hour to 48-hour time window to actually sit down and do the exam. You can do it on paper, you snapshot all the working, and you just send back the working to us on my learning itself. Because at the rate at which COVID-19 is spreading, I don't think we'll be going back to campus anytime soon. Any further questions, any concerns that I need to address? Yeah, I don't know what we're gonna with regard. Hey, will I get any official response for regarding 3020 if the date change and whatnot? Because the last thing I got was, I think, a couple of weeks ago. I don't know if anything else changed. No, I'll check back to see if I got anything. But I think the majority decision was that because of everything that's going on, the date was supposed to push. But I mean, once you guys basically have the report in hand at this point in time, you're pretty much set. You just have extra time in case you need to polish the report if you need to write anything. And they possibly temporarily postpone, but make sure you keep on doing your work in the meantime. So just make sure you have the report already written. Because there's no way for us to figure out how we can get the demos done, and then how we'll actually have you guys present in a reasonable fashion. It just have too many unknowns regarding this right now. Okay, but the only thing I can tell you with regards to this course is until we make final decision as to how you guys are getting tested, then you'll actually know. But you'll know like weeks in advance for when we're going to be doing this. Yeah, I know. It's just some people need access to physical equipment to test and so forth. So yeah, all that is limitations right now. Any further questions at this point? Yeah, it's yeah, I know I forgot to put up the past papers and solutions. I'll start putting them up saying by either the end of the session or either this afternoon or whatnot. Just a matter of to go and get the work laptop and so forth to actually start uploading that. If you guys are actually doing any particular practice for any questions or whatnot and so forth, you can snapshot your work and you can send to me via email. I can always review it. If you guys also want me to do like particular types of questions from the past papers and so forth, you just need to let me know in advance so that I can schedule a session for these guys to do it here online. But yeah, pretty much open until we get some official response to as to what we could do for preparation for this exam. Alright, so that's the end of this session. So until I get some, I'll make sure to upload all the final exams and so forth. And if we're having another session, it's because you guys actually need help with regards to a particular final exam or a certain question, and that we absolutely have to do it online at this point in time. So once you guys email me and let me know, I'll make arrangements so that we can actually do our session online if that's the case. Alright, so I'll see you guys soon, and take care and make sure you guys are safe. Later.